Kia ora, I'm Grace, and welcome back to the third video in this series all about the Borromean rings. In the first video, we looked at how to crochet the Borromean rings and also learnt a little bit about knot theory. And in the second video, we looked at the Seifert surface of the Borromean rings and how to crochet this. If you're interested in either of those topics, feel free to head back to the first or second video before rejoining me here. Now, one question we still haven't answered about the Borromean rings is how do we know that they are definitely connected to each other? And that's what we're going to look at in this video, which is great because not only will that give us some peace of mind about our Borromean rings fidget toy that we made, but we're also going to look into some methods that knot theorists actually use when solving problems. Our main goal here is to show that the Borromean rings are fundamentally different from three disconnected rings. For this to work, we need to find a fundamental quality of a knot that's not going to change when you move the strands around or rearrange it. Then we need to show that the Borromean rings and the disconnected loops differ in this quality. So for example, we might want to find something that's true about the Borromean rings but not true about the loops. So basically, if we find something that's true for the Borromean rings, won't change when you rearrange the strands and try to untangle it, and different for the disconnected loops, that means that they are fundamentally different and therefore you can't untangle the Borromean rings. To illustrate this, we're going to return to our drawing of the Borromean rings. What's fun is we're going to use different colors to do this proof that the Borromean rings can't be untangled. And this is something that real knot theorists actually do. Let's think about coloring our knot diagram. Now, if we look at the diagram, we can see that it is made out of these different arcs or sections of the knot. Each of these can be a different color, and we have a lot more freedom than we would in real life with our actual knot. Here we basically need one ring to be all the same color all the way around, but in the diagram we can have the color changing as the strand passes under another and pops out the other side. We just want to make sure that the strand doesn't change color halfway through. So we could have a lot of fun just coloring in the knot diagram any old color combination, but for this to work we need to be coloring with a few rules. The rules of our coloring are that all three colors need to be used. So in this case we've got green, red and blue, and that at each crossing there must be all three colors or all one color. So this would be okay and this would be okay, but this would not be okay because we've got one green strand and then two blues. That's no good. It either needs to be all three different colors or all three the same color. If our drawing of the knot can be colored following these rules, we'll say that it is colorable. And if it can't be colored following these rules, it fails the test and it is not colorable. The actual colors themselves don't matter. All that matters is whether the same color is being used in one place or another. To check that this is a legit test and the results won't change when you have a knot in different arrangements, we need to check that the results of this test won't change before and after Reidemeister moves are applied. Now, we talked about Reidemeister moves in the first video, so if we want to get a bit more info on those, check that one out to recap. What I mean by this is we want to check that if a knot section only needed three colors to be colored properly before a Reidemeister move, that it wouldn't suddenly change needing four colors. That would be an issue. As well as that, if we had a knot that couldn't be colored and failed this test, we would want to check that after we did Reidemeister move, that it wouldn't suddenly gain the ability to be colored. So we need to check the results won't change before and after Reidemeister moves. Let's start with the first Reidemeister move, the untwist. And let's say we're looking at a section of a knot diagram that is showing a knot that passes the test of colorability. That means that the crossing here is either going to all be the same color or all three different colors. However, if we look closely, we can see that this arc of the untwist crosses over itself again. So this means that the crossing needs to be all the same color. After the Reidemeister move, when we've untwisted the strand, now it's just one strand, so it's still all good for it all to be one color. So that means that colorability passes the first Reidemeister move test. The second Reidemeister move is the pull. Let's say we started off with this section of the knot having crossings that are colored in all three colors. And then after the pull, we want to make sure that the strands that were going off to the rest of the knot don't change color, because we're just looking at a section of the knot here. that means that the two strands are just going to be two different colors. Again, this is all good. This still follows our coloring rules. In this situation, the Reidemeister moves did not affect the colorability. We're just going to now check the second case where this crossing is all one color. This forces the second crossing to also all be one color. After we do the pull, we're just going to have two strands now. Again, we want any part of this that is connected to the rest of the knot diagram to be the same color before and after the pull. So that means these two strands are just the same color, which is the same sort of coloring we had before the Reidemeister move. The second Reidemeister move, all good, hasn't changed our colorability. The third Reidemeister move, the glide, has a bit more going on, as we have three different crossings and a lot of points where this connects to the rest of the knot diagram. Let's start with the example where all three crossings use three colors. After the glide, and keeping all the outgoing strands the same colors as they were before, as they connect to the rest of the knot diagram, we'll see that some crossings now need to be all one color, but again, this is all good. This still follows our coloring rules, so that means in this case, everything is all good, still following our rules of coloring. Now let's see what would happen if we started with one of the crossings being all one color. If one crossing is all one color and it's the central one, that means that after the glide happens, we're still going to have that central crossing being all one color. Still follows our colorability rules, so that's all good. If either the top or bottom crossing is all one color, we can see that after the glide, we still are going to have a crossing that is all one color, and the other ones are following our three color colorability rules. So far, using the third Reidemeister move doesn't change the colorability of a knot. The next thing we're going to look at is if this section of the knot had two crossings that were the same color. We can see that in this case, this forces the third crossing to be the same color as well. So now we just have a section of a knot that is all one color. And after the glide, that's going to stay the same. This means that if the knot was colorable before using the third Reidemeister move, it would still be colorable afterwards. And if it wasn't colorable before, it wouldn't be colorable afterwards. And in fact, we've shown this for all three Reidemeister moves. As any transformation of a knot is made out of Reidemeister moves, this means that if a knot is colorable before you try to untangle it, it will be colorable afterwards. It's not colorable beforehand, it won't be afterwards. So this is something that is fundamental to the knot and cannot be changed with untangling. So now we just need to check if our Borromean rings are colorable and if the disconnected loops are colorable. So we'll start with our Borromean rings that aren't colored in, or the arcs are just black. Let's try to make one of the crossings have all three colors. So let's start with this one. Making that have all three colors has put quite a lot of color into this diagram. Now we can look at how those arcs being colored in affects the other arcs in the diagram. So for example, we can see that this arc here comes to a crossing with the red arc and also comes to a crossing with a blue arc. That means following our crossing rules, it can only be green. Now if we look at this crossing, we can see that we've got green, green, which means the third part also needs to be green, because we can only have three different colors or all the same color. Now that this arc is green and this arc is green, this one needs to be green too. But now if you look, we actually have some issues. We have some sections that break our rules of coloring. We can see that this crossing here has two green arcs and one red arc, which is not allowed. But that's okay, maybe we can fix this. We'll just change this red arc into green instead. So let's check to see the rest of our crossings are okay. Unfortunately, we still have some issues. We can see that this crossing here has two green and one blue. That's no good. And also, this crossing here has two green and one blue. So our only choice is to color this arc green. So now we're left with this slightly sad diagram of the Borromean rings. Now, if you recall, our original rules of colorability were that we had to use all three colors. And in this case, we haven't been able to do that. So the Borromean rings actually fails this colorability test. Let's check if the same holds for our loops. If we have three disconnected loops like this, there are no crossings. So this makes it a lot easier to color this in a way that follows the rules. So for example, we could color them like this. This shows that the disconnected loops are colorable, which is a fundamental property that the Borromean rings do not have. So therefore, the disconnected loops and the Borromean rings are fundamentally different. And so we cannot untangle the Borromean ring. Now this colorability test is an example of an invariant, which is a big idea that pops up again and again in knot theory, but also all over science and maths. Basically, an invariant is a way of simplifying a complicated object like a knot into a more basic idea, such as colorability, where this basic idea tells you something really important about the object. And so it can be useful to help us understand the object. So colourability is an example of an invariant of knots, but there are lots of others out there as well. But we also do this all the time in science and even in our everyday life. For example, speed cameras only care about the speed of your car, even though your car has lots of other wonderful qualities, such as its colour, how many people are in it, the make and model, but the bit of information the speed camera cares about is just the speed. Or if you're trying to get on a ride at a theme park, you might have lots of wonderful qualities, but the only thing that really matters in that context is your height. So that wraps up this series all about the Borromean rings. Thank you for joining me on this journey through crocheting, Borromean rings, surfaces, and colouring. See you next time.